Nature isn't classical, and if you want to simulate nature, you'd better make it quantum mechanical. It's a wonderful challenge, but it's far from easy. These words from physicist Richard Feynman capture the essence of why quantum computers were envisioned, to tackle problems that classical computers simply can't handle efficiently. As Feynman saw the potential, John Preskill from Caltech came up with the term quantum supremacy, reminds us of the reality as in the following words. We hope to develop quantum computers that will really work and change the world. But we're not there yet. This is a marathon, not a sprint. His words underscore the immense challenges and long-term dedication required to unlock quantum computing's full potential. To truly simulate nature's complexity and harness quantum power, we must start from the basics. And at the heart of quantum computing lies the qubit, the fundamental building block. But what is a qubit actually? A qubit is short for quantum bit, and conceptually, it is the quantum counterpart of the classical bit. In classical computing, a bit exists in one of two definite states, 0 or 1, or in other words on and off. A qubit, in a very counterintuitive manner, can exist in a superposition of both states simultaneously. Imagine a switch is on and off at the same time in terms of its functionality. That's right. We can't grasp the thought of it, so it has not got a direct analogy in classical physics. This distinction arises from the principles of quantum mechanics, and this fundamentally changes how we think about information processing. So let's briefly visit the basic mathematical foundation of qubits. A qubit is described as a vector in a two-dimensional Hilbert space. The Hilbert space is a fundamental mathematical structure in quantum mechanics. A qubit can be represented on a Bloch sphere, where its quantum state is a point on the sphere's surface defined by two certain angles. This visualization captures the superposition and phase of the qubit with states 0 and 1, as located at the north and south poles respectively. Having said that, a qubit wave function is represented as follows. Quantum mechanically, the wave function psi is equal to alpha times state 0 plus beta times state 1. Here 0 and 1 are the basis states in two-dimensional Hilbert space. These states are analogous to the binary states in classical bits. Alpha and beta are complex numbers called probability amplitudes, and their squared magnitudes give the probabilities of the qubit being measured in state 0 or 1 respectively. The normalization condition alpha squared plus beta squared equals unity must always hold. This superposition allows a qubit to encode information that spans the space between states 0 and 1, which is fundamentally different from classical computing. Let's also briefly mention the physical nature of a qubit. A qubit is realized by a quantum system that has two well-defined states. There are many physical schemes which are obtainable and conducive to manipulation, at least at the research and primary system level, some of which are as follows. Spin systems are quantum mechanically well known, and the spin of an electron can be up or down considered to be a qubit. Photons are also quantum mechanical particles, and a photon's polarization can be horizontal or vertical to establish the essentials of a qubit. The energy levels of artificially trapped ions, such as the ground state and an excited state, are also promising candidates. Another example is the superconducting circuit states of current that flow in different directions. What's remarkable is that these physical systems are inherently quantum, allowing for behaviors like superposition and entanglement. The question is how we should understand the deep notion underlying these phenomena. The idea of superposition means that a qubit doesn't merely switch between 0 and 1, but rather, it exists along a continuum of probabilities as in the values assigned on the surface of the Bloch sphere. This is not a vague concept, it's rigorously defined in quantum mechanics. Measuring the qubit forces it to collapse into one of its basis states, either 0 or 1, according to the values of the probabilities alpha squared and beta squared. Superposition is not simply both at once in a classical sense. It reflects a new kind of reality that blends classical determinism with quantum probabilities. Entanglement is another profound phenomenon which has no classical analog. When two or more qubits are entangled, the state of one qubit is inseparably linked to the state of the others, no matter how far apart they are. Here, measuring one qubit instantly determines the state of the other, a phenomenon Einstein famously referred to as spooky action at a distance. Entanglement is the cornerstone of quantum computing, enabling powerful algorithms and phenomena like quantum teleportation. The power of qubits lies in their ability to process information exponentially more efficiently than classical bits. A classical n-bit system can exist in one of the nth power of 2 possible states at any given time, and we only need to know the values of the n-bits to recognize the state. In contrast, quantum systems within qubits can be in a superposition of all 2 to the n states simultaneously. This property enables massive parallelism in quantum computations. Before proceeding to the second part of the video, please consider to subscribe to our channel. Once again, as Richard Feynman said, nature is inherently quantum, and any controllable quantum system meeting specific criteria can serve as a qubit. But not all qubits are created equal. For efficient quantum computation, qubits must meet key requirements. Here we explain those in a nutshell. Coherence time is a critical key factor. Qubits must hold their quantum state long enough to perform calculations without losing information. Another key property is the gate fidelity. Precise quantum gates are essential to minimize errors during operations. Scalability is also an imperative requirement. Solving complex problems demands thousands or even millions of qubits. High connectivity level among the qubits is another desired quality. They must interact efficiently to enable entanglement and multi-qubit operations. Error correction is paramount and absolutely necessary for the fragile and large qubit systems. Physical qubits need to support encoding into error-corrected logical qubits to reduce inaccuracies. Quantum error correction protects qubits from decoherence and errors by encoding information redundantly across multiple qubits, ensuring reliable computation. The speed of operation is another aspect of a quantum circuit since faster gates reduce errors from decoherence. Lastly, maintaining initializability and readout fidelity is an imperative metric as well. Qubits must start in a known state and provide accurate measurements. These factors collectively determine whether a quantum computer can implement the complex algorithms needed to solve real-world problems. The journey is ongoing, but each step helps researchers to understand the nature of qubit implementation and discovering the transformative potential of quantum computing. No single qubit type satisfies all quantum computing criteria perfectly, but each excels in specific metrics. For example, trapped ion qubits lead in coherence time exceeding minutes level, with gate fidelities over 99.9% and offer precise readout. Superconducting qubits dominate scalability and speed, achieving gate operations in under 20 nanoseconds and integrating thousands of qubits. Photonic qubits are promising since they excel in connectivity via fiber optics and boast long coherence times and fast operation speeds, as well as room temperature operation unlike qubits operating at cryogenic temperatures. Trapped ions provide unmatched stability, superconducting qubits drive error correction with fast operations, and photonics enhance long-range communication. There are several other promising research topics such as nitrogen vacancy qubits and topological qubits to be employed in quantum computer architectures. Hybrid systems blending these strengths could pave the way to fault-tolerant quantum computers, bridging the gap to real-world problem-solving. A qubit is not just a fundamental unit of quantum information. It's a gateway to a new computational paradigm. Its deep nature blends the principles of superposition, entanglement, and quantum coherence, challenging our classical intuitions and opening doors to transformative technologies. Research teams continue to refine the ability for manipulation and integration of qubits to scale quantum systems and push the boundaries of our understanding of the universe. This is the end of our video. Thank you for tuning in. Until next time.